Right. So yes, more on the technical side. In this presentation, I will just provide an update on the progress we've been making on the application of outbreak detection algorithm to antimicrobial resistant surveillance. So right. So right. Can you see my slide? Right. Yeah.
Yeah.
Perfect. So yeah, we all know the importance of early detection for antimicrobial resistance, because of course the earlier the detection, the better potential for early intervention. So that makes developing tools for surveillance quite crucial. Now, the objectives in this project that actually that we've been carrying on were two. First of all, to review and improve the quality of the collected data, which comes from clinical scanning surveillance program through England and Wales, and referred to the years 2010 to 2021. And then the other goal was to develop an automated analytical system based on the Farrington algorithm to provide alerts for potential outbreaks or changes in resistance trends by periodical analysis of the surveillance data. So what I will be focusing mainly in is then the Farrington algorithm. So what is the Farrington algorithm? It is essentially a tool for spotting unusual patterns in data. So you've been given a time series of data that's in the case of antimicrobial resistance in our case are just a time series of positive tests, and the algorithm detects detecting outbreaks or unexpected trends in the data. To be more specific, how the Farrington algorithm works, it works essentially in 4 steps. In the first step, what you do, you just provide, you feed historical data into the algorithm. So you will feed all your set of positive test cases. In step 2, the algorithm crunches the numbers, so analyzes the data looking for patterns. More specifically, what it does in this step, it fits a linear model to past data. And then in step 3, it detects anomalies. So it identifies unexpected increases or spikes in the number of positive tests. And this is done essentially by defining a threshold based on past observation. And in this figure on the right, a typical output given by the algorithm is shown here. The color curves are just time series of positive test cases for different drugs, and the algorithm provides a threshold to dash the line, and in step 4, what it does in step 4, it raises an alert every time this threshold is crossed, which marks something unusual, which is worth of further investigation. Right. So this is essentially, in a nutshell, how the Farrington algorithm works. And what the goal was to apply then this algorithm to antimicrobial resistance data, and we had data from cattle, pigs, and chickens for the years 2010 and 2021. And we looked at the resistance developed to the following set of antibiotics. This that you see in the table, these are 24 antibiotics which we investigated. Okay, so this data set contains information, in the data set what we have the month, of when the test is the sample has been tested, the year, the month and year of submission, the location, the livestock species, and also the bacteria species. Then the data set is also aggregated to provide across England and Wales to provide monthly counts of resistance tests for each drug and for each animal species. And the thresholds are then calculated for each drug by the algorithm. Now, in some cases, though, this is a limitation of the algorithm. Of course, if you don't have a rich enough data set, historical data set, then the algorithm is does not provide reliable output. So in the case of, in our case, for example, for penicillin, we didn't have enough number of tests, total tests, and also number of positive tests. And for this in these cases, these drugs were omitted from are omitted from the analysis. Right. So what we specifically looked at then at two different implementations of the Farrington algorithm. So the Farrington algorithm can be applied straightforwardly to the time series of your positive tests. I mean, the test that gives you a resistant result in your sample. Or you can apply the Farrington algorithm to the rates of events. So in this case, you look at the ratio between number of positive tests and the number of total tests performed in a given time window. In our case, the data are given monthly, so the time window is always a month. Right. So in the case of the first type of implementation that I just mentioned, this is this plot here shows what the algorithm outputs. This is this output refers to samples taken from chickens, and for these three specific drugs, ampicillin, doxycycline, and tetracycline. So, as I said, we have a data set from 2010 to 2021. So what the algorithm does, it uses the first 5 years for training, and then it outputs, it calculates a threshold, which in this case, which is shown here by the black dashed line. Now, on the vertical axis, we would have just the number of positive tests, but for visual representation, we had divided that by a factor so that the threshold, the dashed line, is just a straight line. This is actually what the algorithm produces. To be more precise, is a varying threshold in time, but for visual representation, we introduce this factor just to have one straight line as a threshold. And so again, each crossing of the threshold here marks a flagged event, which is worth which is set for further investigation as a possible outbreak. But as I mentioned, this plot I just showed, it refers to a standard application of the Farrington algorithm, where we consider where the algorithm is fed only the number of positive tests. But this implementation actually works well when you have a fairly uniform number of testing frequency. So if your number of tests is fixed in a time window, but the data set we had actually had a very quite varying testing frequency. So that affects of course it introduces a bias in your result, because of course if you have more tests, you have also more opportunity for positive test results. In order to compensate, partially compensate for this bias, we consider the second type of implementation of the algorithm, in which, as I mentioned already, what we apply the Farrington algorithm not to the number of positive tests, but to the rates, so the number of positive tests divided by the total number of tests performed. Technically, this implementation is achieved by including what is called the population offset. So, but this is it just equates to what I've just said. So we apply the algorithm not to the number of positive tests, but to the rates, so the number of positive tests divided by the total number of tests. And here I show you what a comparison between the two implementation. So the plot on the left refers actually to cattle and to the spectinomycin drug, and the red line is the standard implementation of the algorithm, and the blue line the implementation with what I call population offset. And as you can see already visually, the blue line actually produces tend to produce less. In this case, produces less flagged event, less crossing of the threshold of the dashed line as compared to the red line. But to have a more quantitative assessment of the different performance of the algorithm, we also looked at the measure of difference between the model and the data. And the black line here in the plot on the right, sorry, it refers to the the standard implementation of the Farrington algorithm, and the red line to the implementation with offset. And you see that the red line is actually lower, means that is closer to what you to the data. So essentially what you see on the right is a measure of the discrepancy between model and data, which shows that the modified Farrington, including the offset, is closer to the data. And I show you also another case here, always in cattle, but for ampicillin, where I still compare the two implementation of the algorithm. So you see that with the blue line in this case, though, has more actually crossing of the threshold. So, but still, if we look at the measure of difference between model and data, is always the implementation with the offset is always closer to the data. So, essentially, what we gain from this different implementation, we gain an implementation of the algorithm that is quantifiably closer to the data, and which tends therefore to reduce, not only to reduce the false positive, but also to flag events which are not would not be flagged by the standard implementation of the Farrington algorithm. So to conclude, we consider the Farrington algorithm, which is applied to antimicrobial resistance data. This is a commonly used tool for early outbreak detection, and applied to antimicrobial resistance data is a tool that help us flag suspicious case increases in of resistance for further investigation. And then what I show is that introducing a population offset improves the performance of the Farrington algorithm. It increases the ability to avoid false positive in outbreak detection, but also provide extra confidence that the flags being raised by the model are showing true increases in resistance. Okay, with this, I think I can conclude here.